Same shit.
Beach yesterday.
Did you?
Yes,
Bondi.
Oh.
Isn't that a pack of people?
There was a shark.
Oh.
아빠 아는 사람이었어.
Oh.
So I'm looking at my jungle sticker collection.
Cute. Yeah, you gotta use it and don't keep it in your pencil case. Okay, welcome back, year 12. Now you're officially year 12. You're like in schools and the systems as well. Like, so we briefly discussed about the annual schedules that you will need to fill up your UX applications in probably July. I mean, you got to think about what courses in university, in which university you want to do. Okay, got a plenty of time, but have a think about what you want to do. I know you've got running out of time later on too. Okay, all right. For the assessment, yes, you most likely all of you finished your first assessment in your term 4. The second assessment coming up depends on what modules, but if you're doing module 6 in your schools, more likely you will get a titration prac or like some assessment related to titration practicals. In term 1, so which is 2 to 3 weeks, we are going to do many pracs, many titration in the lab today. Okay, so I will ask you to do like a performing. We actually done once, like doing SNM-based titration. You see there's some color changes that. I will actually give you a school exam question that's in the exam settings, which is only running for 40 minutes. So you need to finish the prac in the 40 minutes, and sometimes you need to finalize your calculation in the 40 minutes too. Which means that you really need to understand why you're doing the prac. You need to understand like how to do performing the calculations as well too. So I'm gonna quite rush on chapter 1 and 2. That I'm skipping some of the indicator question, indicator prac the way we have in the chapter 1. But let's talk about some acid and base. Oh, okay. Before we talk about acid and base, it's been a while. Shall we revise a little bit of module 5? Okay. Don't worry, I'm not gonna ask you many questions because I don't expect you to remember all of them. Module 5, equilibrium. Okay, module 5 is about equilibrium. As you remembered, okay. Let's think about what are the conditions for the to achieve that something we've known as chemical equilibrium. Okay, we need to have a reaction that is reversible. Okay, that after that we have also reactants, the product reactants. They reach the equilibrium by looking at that there is no change, or we say the constant concentration of the both reactant and the product side. So we see like they're kind of stopped, but in fact they are dynamically exchanging. So we call that as the reaction rate are the same. And we went through many questions about the definition of the equilibrium using the graph, using the modeling. One modeling I used was like 2 beakers exchanging the water. So you see that there's no change in water levels anymore too. I showed the YouTube video like we couldn't really do using the straws to migrate the water from the measuring cylinder. You see that no change in the water levels anymore too. So those are the ones that's describing the equilibrium. We call it dynamic equilibrium. And we also learned about Le Chatelier's principles. Chatelier's, in short, like LCP. I hope you have a definite, good definition about Le Chatelier's principles. Anything the key word for that is if there is any change in the equilibrium, it'll make a counteract, act the change to reach the new equilibrium. Okay, and we related that to something known as the collision theory as well. Do you remember the collision theory? Okay, the condition for the collision theory too. So, according to based on the Le Chatelier principle, we can have a few changes in the equilibrium systems. Okay, what have been the one change that we consider in the equilibrium system? Yes, any changes? We can have a change in concentrations. Good. Give me one more. Yep, concentration, change in temperature. And the last we have come up with the pressure. These are the three things that we consider about changing the equilibrium system, especially the temperature. We spend quite a lot of time to study about the temperature because we have a two effect of the increasing and decreasing temperature. One is it will affect the rate of reaction. The second is it will affect the shift due to that, whether that is exo and endothermic reactions too. It's a good revision. Just try to bring it out all together because later on in module 6, we're going to come back to the module 5 contents because we're going to talk about something known as equilibrium constant. Okay, Haley, what is the equilibrium constant? In other words, K. What's it K equals to? Or KEQ, I should say. Oh? Hannah? Yeah. Yes, thank you. Product on the reactant concentration. That energy is about the delta H. Don't worry, we're going to talk about the delta H today as well too. Okay, so KEQ is simply it's describing that the rate. Oh, sorry, the concentration ratio between product and the reactants. So you want to know when the KEQ is high. So remember that at the equilibrium we do not have any changes. So it's kind of appeared as in the high KEQ that at the equilibrium state, which is not really changing it, we have lots of the products remained compared to the reactants. When the K values are small, that means we have a lot of the reactants remained rather than products. So that is related to something we know as KSP later on too. That is known as the solubility product, specifically talking about dissolving the salt or the ionic compound into the water. Depends on the solubility. Do you remember like its solubility? Solubility is all about up to how much can be dissolved. Okay, so we have a unit of the grams per liter. Means when I said 1 gram per liter means we can only dissolve up to 1 gram per liter. Okay, that's how you need to understand about solubility, and we kind of explain you lots about the main difference between concentration and solubility. They are sharing the same unit, but talking about quite different things. Okay, we also talk about molar solubility. Say 1 mole per liter is a unit of the concentration, but when we say 1 mole per liter in solubility, it simply means we can dissolve up to 1 mole in a 1 liter. Okay, and depends on that will determine the KSP value. Having the lower molar solubility means that the ionic compound doesn't have much capacity to get dissolved in the water. The KSP will appear as really low values. In other words, more likely they can form the precipitate in the water forms too. So I kind of described that in your formula sheet as a cheat sheet. All of those ionic compounds in the formula sheet, they're known to be forming precipitate or not dissolved they're not really dissolved in the water well. Okay, this is where we're up to. Quick summary of the module 5. Can you picture that the big picture of the module 5, like thinking about some of the things we learned? The homework I gave you was the past HEC questions, by the way. So you will probably see like all the questions related to these topics too, maybe some more extra. Okay. Now let's move on to module 6. That is talking about now specifically acid and base reactions. Now, before we move on to the chapter 1, let's revise a little bit of something we learned, probably you learned in year 10. Yes, Haley, year 10. It's a very simple question. Those of you who learned the chemistry in mainly in year 10 or even though, I probably ask you to memorize some templates of the chemical reactions. Okay, as in what if we have something called acid plus metal hydroxide, that's a base. I ask you to memorize what are the products of those type of reactions. Okay, salt, it's basically salt and the water. You don't have to really think about in here once you know, this is basically just, we have an acid, we have a base, they're producing the salt and the water. We also have something like reaction between acid and metal carbonate. or the hydrogen carbonate? Anna, what is the reaction between the product between acid and metal carbonate? Salt, carbon dioxide gas, and the water. Again, you should not think about what are the products are, because it is a kind of pre-OSHEM knowledge before we started module 6. Teachers and examiners were not kind enough to explain you that again too, because pre-OSHEM knowledge. So if you haven't taught about this yet, just memorize that as we have an acid, some metal carbonate from this. Okay. We also have acid that's reacting with the metal, that's the solid metals, salt, and the hydrogen gets very good. And it's essential to know that what are the products, like how do we determine the presence of the carbon dioxide and hydrogen gas. CO2 can be tested by using something known as a lime water experiment. H2 is determined by the pop test too. So that's something we learned in year 10. Okay, nothing really fancy. And this is kind of given as a template that once you know what your reactants are, then you should know what the products are straight away. Okay, 3 typical types that you should know before we start chapter 1 and chapter 2. Any questions? Examples, if you wanted. HCl, aqueous, react with the sodium hydroxide. See that? As soon as you see that, you get the NaCl, aqueous, and the water. Aqueous there. Okay, metal carbonate, HCl, aqueous plus the sodium carbonate. Let's say solids. They form the sodium chloride again. That'll be dissolved. H2O and the CO2 gas. Balancing is something, just the basic, the essential now. HCl acid plus the metal. Let's say we say Mg, magnesium solid, forming the MgCl2. That's aqueous or the solid, depends on how much we have, and H2 gas. That's how you need to use your templates to figure out the products are. Okay, nothing really serious, nothing really fancy. Just use that. That's all I can say for now. Any questions about quick revision on the year 10, some reaction templates? Everyone good? Okay, Rachel, you good? Okay. So why then, let's have a think of the definition of the acid, something we didn't really cover in the year 10 or year 11, starting from the year 12. Okay, I give you some examples of the acid. Let's move on to chapter 1. Okay, page 2, please. When we say acid, there are a few acids that you must memorize in chemistry, and they are quite simple to memorize too. Can I erase that now? Okay. So common acid acid that we use in everyday life and also use in the school laboratory is started from hydrochloric acid, which is HCl, sulfuric acid, H2SO4, nitric acid, HNO3, ethanoic acid, or known as acetic acid, CH3COOH, carbonic acid, H2CO3, phosphoric acid, H3PO4. So you need to memorize at least 1, 2, 3, 4, 5, 6 acids. Okay, you do not need to memorize the citric acid, C6H8O7. In some school trial papers, they give you citric acid a lot, but it doesn't mean that you need to memorize the chemical formula of it, because it's quite complicated, complex organic acid. And same for the vitamin C, you don't really need to memorize the chemical formula of that too. But just need to understand that, oh yeah, okay, citric acid, something that sourness in the fruit or the food, it actually comes in the acid forms too. Vitamin C, or it's also known as ascorbic acid, is also being an acid type now. Now, it's good to know some everyday use of those acids. You are carrying hydrochloric acid in your stomach. How do you know? When you get a reflux, when you're vomiting, you get some burning sensation on your throat. Why? Because of the hydrochloric acid is so acidic, it's kind of burning, it's kind of damaging your throat. So if you're vomiting a lot, that means you get a more damage of that too. That is permanent damage could be induced. Sulfuric acid, we use that for many purposes. It's actually used with car batteries, detergents, fertilizers, a lot of too. You probably haven't heard like a sulfur. You can actually find the fertilizer in the Bunnings warehouse if you give all that. You can see some chemicals that we are talking about in here. Nitric acid used for the fertilizer, dyes, and explosives. Acetic acid, it's just simply a vinegar. Yeah, so you are consuming some vinegars in many like a food, some other things, even the snacks. There are manufactured glues and the plastics used there for too. Carbonic acid, when you're drinking your soda, that you're basically drinking some carbonic acid too. Okay, this is why some of the soda, like many of the soda, they taste a little bit sourness. Not there's a hint of sour. Okay, phosphoric acid is basically flavoring and the use of fertilizer, citric acid, and vitamin C. We talked about it before too. Okay, now one thing that common in all of these hydrochloric acid, or also all of those acid is, you will see that they are all having hydrogen. Okay, this is something that's very important to identify. This is acid or not too in chemistry. Acids generally involved with some of the hydrogens. So, and we're going to talk more about the definition, the correct definition of the acid later on too. Now let's look at some common use of the bases. Next page, please. We see that some sodium hydroxide, ammonia, calcium hydroxide, magnesium hydroxide, sodium carbonate. These are the known as the common bases that we're using in everyday life. Yes, you need to memorize them too. It's not that complicated. Anything with the hydroxide, guys, so just think simple here. Anything with the hydroxide more likely be a base. Anything with the carbonate, we're working as a base. Exception is the ammonia. It does not have any hydroxide or the carbonate, but still working as a base. This is something that we're going to talk about a lot today. Okay, and we have many uses of that. Sodium hydroxide, for example, we use that for the oven cleaner. And something like bleach is also made with the sodium hydroxide too. So I want you to think about how to determine. So assume that we have an unknown clear chemical, clear liquid. You don't know whether that's acid, base, or water. Okay, Richard, how would you test that? How would you test that the clear water is maybe an acid, maybe a base, or maybe water? How would you taste it? How would you not to taste it? How would you test it? pH. Okay, you're using some. If you have a pH meter, you dunk the pH meter into that, and then you see the pH change. So if the pH below 7, what is that? It must be the acid. If the pH is above 7, that's the base. That's a common knowledge that we're using everyday life too. pH 7 is mostly like a neutral, so it's most like a water. Any other method to test for the acid and base of water, Steph? If you were given a clear water, what would you do to figure out whether that's acid, base, or clear water? You can react with something else. That's a fancy, but something that we don't do. We can do many methods. We can use indicators. We can use pH meter. We can do the reactions to figure out whether that's acid and base. But something we never ever do is we do not use your body to test for the acid and base. I'm saying you do not taste it. You do not smell it, Haley. Don't smell it. Don't taste it. Don't touch it. Okay? Because what happened here is when you touch or taste, when you eat, this is what happened. We called acid and base are highly corrosive. Write it down, please. Highly corrosive. I briefly talked about why you get a burning sensation when you're vomiting, because hydrochloric acid is highly corrosive. It's actually burning and damaging your throat, the skin cells, or the throat cells. Okay, so this is what you get from the hydrochloric acid. That's what you get from sodium hydroxide. You never put your hands to bleach. You never put your hands to oven cleaner, the bare hand, because you know that you get damage of your skins. Not only the damage, you can make severely and burn as well too. So, or you do not smell the hydrochloric acid, because what happened is the hydrochloric acid comes along with the chlorine gas. It's going to convert it into the hydrochloric acid in your lungs. It's going to melt into the lung alveoli cells. So you get a severe damage. This is why you need to wear those PPE, the protective gears, including the gloves, lab coat, closed shoes, something that's very important because you get a spillage, then you get a burned. Okay. Sometimes you may need to wear the mask as well too if it's dealing with some combustion of that. So this is something reason why we never boil the hydrochloric acid. I don't want to get the chlorine gas all around in this room so that you get lung damage. So when you're dealing with the acid and base, which we're going to do in a few weeks, never just try to with that because sodium hydroxide or the base is actually quite slippery, like a soap, basically. But it doesn't mean that you put your fingers there, feel that texture of the chemical. Oh, this is slippery. This must be a base. You can't do that. Okay. Or you see that you see this damage of your skin. It's like, oh, this is damaged. This is damaging my. It's hurting my the fingers. This must be acid and base. You never do that. Okay. You never taste it. I know acid tastes like a bit of sourness, and base tastes like bitterness. If you ever tried to, I would say like who do, but like if you ever ate soap before or shampoo, accidentally, taste of bitterness coming out from this from the base properties too. But I said, never ever trust that. Never trust your body. So instead of we using the body parts, we're using something called indicators to figure out whether that's acid and base. pH meters are good, especially digital pH meters. They are most reliable tools that we're using to determine the acid and base because it shows the number, which is the pH. So I see that below 7, there must be an acid. Above 7 must be the base. So naming of the acid and base, let's skip that. I mean, that's common thing with page 8, please. So for the common properties of acid, as you can see, like from here, the sour taste, conducting electricity in the solutions, turning blue litmus to the red. I call it a bar. Okay, the bar stands for blue to red for the acid. Okay, bar is how you can remember. The blue acid, blue turns to red and acid, and for the base it would be RBB. Okay, so it means red turns the blue to the base. Just simply memorize a bar. How easy is that? Okay, bar stands for blue turns to red in the acid. That's all you need to do. That's how we use the litmus paper or litmus solution to figure out whether that's acidic or the basic. The solution must have the below pH 7 for the acid, and for the base, soapy feeling, kind of slippery feeling, and also have the bitter taste, but you never taste that. You never taste your bleach or the open cleaner. Conducting electricity well and turning red litmus to blue, and that's something we can determine there. We call like an acid and base. But limitation here is we wouldn't know the very specific pH, how strong that acid and base is, how dangerous that. So we can, even the acetic acid, which is the vinegar, can turn the red litmus to the blue. Okay, but you never know. There might be a hydrochloric acid that you have in the beaker. So this is the reason why we're using the very specific indicators, which are these, with this very specific pH ranges given here like that. Do you remember in the titration practice we did in before? Okay, also some of the experiment. I show you that the one chemical solution changed the color from the colorless to the bright pink. Okay, there was actually indicator called the phenolphthalein. You would say that the pH, the color change of the solution from colorless to pink when the solution is, when the mixture is pH above 9. That's what you try to say. So that means pink is above 9. Below 9, you would say colorless, colorless color of the solutions. So why do we use those specific indicator? Because each of the indicator has very specific pH ranges too. This tells you that not only whether that's acidic or basic, this tells you the actual range of the pH of the solution you have. So you're going to use the phenolphthalein quite a lot. You need to memorize everything here, including pH range and the color changes too. So for example, methyl orange has a pH range of 4 to 6. Before that, reaching the weak acids, before the 4, it shows the orange color, and after, above the 4, it shows the color to yellow. So when you see that methyl orange changed the color to yellow, you need to know that that must be pH above 4 now. Does it make sense? Or in between 4 to 6. Same for the bromophenol blue, which has a pH range of 6 to 7. Before the 6, prior to 6, it shows the colors of yellow. After 6, it turns the color to the blue. So when you see the blue color from the bromophenol blue, you know that that's close to the pH 7. It's quite close to pH 7. So it might be safe to drink in some cases. Thymo blue. Oh, by the way, these bromophenol blue or thymo blue is something we're using in the swimming pool quite a lot too, to determine that the pH range of the swimming pool, which is ideally it needs to be 7.2, so that it turns the color to blue. That means you're safe to go into the swimming pool. If that color is yellow, you're there not to go in there. That's due to some of the heavy rainfalls, by the way, because the rainfall kind of drops the pH quite severely. Thymo blue has a pH range of 8 to 9. So you see that before the 8, it was yellow. Now it changed to blue after the pH 8. Okay, and then phenolphthalein, I talked about it. Arizoline yellow, 10 to 12. So it's testing for the really high the basicity, like alkalinity. So the yellow before the 10 and red after 10. So the reason why you need to know, because you actually get questions like, you are given a solution. Then you will be asked to, which is the most suitable indicator for that? It will be 1 mark. For example, I have a solution that pH of 10. Okay, assume that I have a solution of pH of 10 from my digital pH meter. I just want to clarify that whether I'm using the indicator. So what would be the most suitable indicator to use if I have a pH 10 solution? I would not use anything below the 10. So I can't use methyl orange, nor the bromophenol blue or thymo blue, because they won't test for the pH 10. So the good option is probably start with the phenolphthalein. But if you want to make sure like that's a pH 10, I'll try it again, conduct another experiment with Arizoline yellow. If pH 10, that solution changed the color for both of the phenolphthalein and Arizoline yellow, means that it must be in the range of pH 10, something about pH 10. Does it make sense to all? Okay. Yes, you need to memorize those names and that, but not yet. Not yet. I will go through some titration prac later on too, and we're going to go through some questions related to the indicators. But you will need to memorize everything in here. There'll be some indicators like bromothymo blue is another example we used to, but we're going to discuss that a bit later too. Okay. So why is these indicators important? Instead of using your bodies, you smell it, you taste it, you touch it, simply using the indicator means that you can determine whether there's an acidic or basic. So even though we don't know what the solution is we have, by just put some indicators in, we know that's having the acidic property or basic alkalinity property too. And that's been used for many, many, many years, like maybe like 100 years, 200 years. Ancient Egyptians, they knew how to use those indicators because they used something known as the natural indicator, which is look like this, page 11, the red cabbage indicator. So from the human history, where people knew that how to test for the pH, or they didn't specifically know about what the acid, what the bases are, but they knew how to test for those, like something higher, something ideal, the conditions they want to reach. Red cabbage, not only for the red cabbage, anything with the purple, anything with the black colors, like in the colors of the fruits or veggies, for example, blueberries, red cabbage is one, beetroot, they all have the similar properties, which means depends on the pH they're in, the solution they're in, they will change the color depends on the pH. So red cabbage color itself is a kind of purple, but when you make a solution, you basically chop the red cabbage, boil it, you get the solution of the red cabbage or red cabbage water, put some chemical like acid and base, you to see that depends on the pH, it changes the color from red to kind of greenish yellow. Okay, in the middle, blue means like kind of purplish blue, or the blue, it means like in a pH 7. Okay, red means it must be the acidic pH 2. So the reason why we're using natural indicator quite a lot even now is because it shows a very specific ranges, even numbers of the pHs quite accurately. This is the basis of something known as the universal indicator. If you've ever seen the universal indicator, that kind of comes in the purple, the same color as the red cabbage color too. So that's kind of artificially made natural indicator, or artificial indicator. that shows the color changes depends on the what pH they have to. Okay, so this has been used for many years, from maybe it's probably like 1,000 years, maybe more than that. Okay, so people knew that how to use a natural indicator to test for the acidity or basicity, even though they didn't especially know what the definition of the acid and base. And the people thought about, especially scientists in 1800s, they started thinking about, hey, I have some changes of colors from like for the red cabbage, from blue to red. Okay, and they just want to kind of test for that. What makes the change the color? What makes it change the blue to red or blue to yellow in the natural indicator? This is where we started like a definition of the acid and base on the next page. A scientist who actually started learning about, investigating about acid and base, it started from the Lavoisier. Okay, so let's write it down, Lavoisier here. What I'm going to do in the board here is I'm going to write their definitions of the acid and base and also the limitations. It's very important to know the limitation of each of the scientists or the scientific models, because the modeling or the science theory is kind of developed by investigating the limitation of the previous models. So Lavoisier is the first one that pioneer of the investigating acid and base. So what he defined about acid is, he defined that as something that acid is something. He didn't especially know about the chemical, something that contains the oxygen. He thought about it's got to deal with something with the oxygen, because he was a pioneer. Like, he actually investigated quite a lot of oxygens in his experiments, and he saw that some of the oxygen-contained chemical changed the color of the natural indicator. So, okay, so all of those, like having the oxygen change the color from blue to red, so it's kind of indicating the acidic. So it's also given on your second dot point in here. Okay, he observed that when dissolved in the water, phosphorus and the sulfur oxide made the acidic solutions. So it's basically related to the sulfur and the phosphorus. Because what we know now is when you're putting the sulfur and the phosphorus into the water, they're forming something known as sulfuric acid and phosphoric acid. So, which in some sense, it is right that oxygen is kind of involving in forming the acid too. But he didn't really call it the bases. Okay, let's talk about the bases too. The other portion of the compound which combined with the oxygen to form the acid was called the acidified base. This third dot point. So let's write it down. Acidified base, something that combined with the mixture of the sulfur and the water, or the phosphorus and water. Limitation. What would be the limitation of that? There will be many chemicals, I should say many acids, without the oxygen. There are so many of those. For example, even we know like hydrochloric acid, it doesn't have the oxygen, but it's still working as a strong acid. Okay, so that's something that left at the limitation. So it's kind of the first pioneering work, and move on to the next scientist. So it started from 7. Okay, let's write it down the year. It might be helping too. You don't really need to remember the year, but just giving you some timeline of that. Okay, next person is known as Davy. Davy is investigation in 1800s, so 1810. Okay, in Davy's definitions, he described the acid as something that, dealing with acid, is something like containing the hydrogen. It didn't specify like what hydrogen, like just simply saying hydrogen. So as you can see, like hydrogen, he has to figure out the reaction between some acids and a metal forms the hydrogen gas. So that's what he used to back it up his experiment. That where every acid reacting with the metal producing the hydrogen gas means that acid must have some sort of the hydrogen itself. Okay, so using the acid and the metal reaction. So it's more developed from the Lavoisier's the definitions that is start to talk about like some specific chemical reactions, which is more scientific, something we believe in now. And he also proposed that when acid is known as an acid, is working reacting with the base, the famous the reaction type produce salt and water. This is coming out from the Davis experiment too. So it's about the metals and that it's very useful, but limitation is there are many. It's actually the last dot point here. He did present many problems, including that there are many hydrogen-containing compounds which are not acidic too. So there are many compounds containing hydrogen, but not working as an acid. What about the example? Methane, CH4. It is not working as an acid because it's simply methane gas. Any of the kind of carbon mixtures, they were not working as an acid at all. So that's left as a kind of limitation of Davy. Okay, so next person comes along to figure out and improve that limitations. The third person is known as, his name is Arrhenius. And in 1884. So you can see like it's almost like a 30 years difference between quite a bit of years. It's also related to the development of the technologies that they had at the time. Okay, development of the some extracting some chemicals at the time too. So as we developed the technologies, they were able to get the better definitions as you go. Oh, it's the same for the now too. So he's the first one saying, oh, acid is something that's releasing or the producing hydrogen ion in water. Now, think about what I mean by H plus and difference to the H. Bit of basic H and H plus. H is known as the hydrogen atom. H plus known as hydrogen ion. As you remember, like from the year 10, year 9, year 11 too, hydrogen ion means that it already lost an electron. So kind of having positively charged. And if you remember that, in your periodic table, so hydrogen is number 1. It does not have any neutron. I'm simply, so this is why I use the word proton to describe the hydrogen ion. So every single time you see the hydrogen ion from now, I'm going to use these two because hydrogen does not have a neutron. So when you lost the electron, it only remains the one proton in it. Does it make sense to all? So Arrhenius believed that, and he kind of he actually performed many experiments at when you put the acid to the water, they release the hydrogen ions, and he defined the base as is releasing the hydroxide ion in water. And this explains quite a lot of the acid and base reactions. So for example, when we have like a sodium hydroxide and hydrochloric acid, okay, there's a neutralization between those two, okay? Or when we're thinking about hydrochloric acid into the water, they release that into the hydrogen ion plus chloride ion and leaving that water like this. Okay, so that's what he believed about like the acid according to Arrhenius' definition. Sometimes these two, H2O and H plus, get combined, forming something known as H3O plus. This is known as hydronium. ion and leaving the chloride ion like this. Okay, it's important to know that the amount of the hydrogen that produced is always the same as the amount of the hydronium ion. So sometimes we say the concentration of the hydrogen ion is same as concentration of the hydrogen ion too. We're going to come back to this when you talk about the calculation later on too. So don't get confused about hydronium ions. It simply means hydrogen ion combined with the water, which it has the same concentration as the hydrogen ion. Does it make sense? Okay. So this quite fits to the many of the chemical experiments that even now we're performing too. So the definition is quite rigid and quite also be quite flexible, but the limitation is quite clear. Because when we're looking up the definition of the Arrhenius, it must be related to the water. Okay, so the limitation is it's only limited in aqueous solutions, which means we could have something like comes in the gases or the solid that still can be working as the acid and base. So it could not explain any other states. The acid, no, the base. Okay, so for example, I bring up the CH4 gas. What could not be explained by using the Arrhenius? He could not explain why the CH4 is not releasing that. And another example is NH3, ammonia gas. When we test that, ammonia gas itself carries some alkalinity or like a basic property, means it turns the color of the nature indicator to more like the yellow or the green. But according to Arrhenius, because he's only limited in the solution or the water, the gaseous state of the ammonia could not be explained. Why would it change that color of the nature indicator? He could not explain that. Okay, but in our days, even now, how many years from there to 1884? It's about almost like 230 years. Okay, we're still adopting some of the Arrhenius definitions that because it's so useful to determine about like an acid-base reaction in school laboratory. That base reaction between solution to solutions. It fits in. It explains really well that acid releasing the hydrogen ion, base releasing the hydroxide ion in the water. Okay, but it needs some development to overcome the limitations. So the last definition is by two scientists that's known as Bronsted-Lowry definitions. They're in 1923. So it's been almost like 100 years, 101 years now, 100 years. So this is 100 years old definitions now. Even these days in contemporary chemistry, we're still adopting that. We still use quite a lot. We have a better definition of acid and base, which is in the organic chemistry, but we don't really talk about it in today. Okay. So we're going to focus more on the Bronsted-Lowry, that they define that acid as something that's known as H+, which is proton donor. Rather than just speaking about this releasing the hydrogen ion, they describe that as acid is something that's eager to donate the hydrogen ions, which is a proton. While the base is something known as hydrogen proton acceptor. Okay, so this explains quite a lot, almost everything about acid and base reactions now. The limitation is, we're going to talk about limitation a little bit more. Some of the acidic oxide plus basic oxide, something does not have any hydrogen, still working as an acid and base from the nature indicator, could not be explained. But let's talk about like some privilege or like some using that Bronsted-Lowry definitions to explain the acid and base reaction that we learned. So, on your page 16, let's go through the examples that we have. Let's use the Bronsted-Lowry's definition to explain that. So what we have now is we have hydrochloric acid, that's a gas. Again, Arrhenius couldn't explain that the gas state property because it's only limited in the aqueous, the water. But when they put that into water, the liquid, we got to think about it in here. I ask you to memorize that, some acid. So HCl is simply hydrochloric acid. We know this is the acid. So as soon as you see the acid there, you got to think about this is your proton donor or the hydrogen ion donor. What that means is this hydrochloric acid will be kind of split into H plus and the Cl minus. And this will be donated into the H2O. Okay, that means that this will be working as proton acceptor. So as water, H2O, received accepting the hydrogen ion, it becomes to H3O plus. I call that again. This is known as the hydronium ion. Okay, leaving that chloride ion itself. So instead of talking about hydrogen or hydrogen release or the hydroxide release, when they started talking about hydrogen accepting, hydrogen donating, it's much better to explain some essence of the acid and base reactions. So the only thing we need to do is we need to figure out which is working as an acid and base then. Okay, or by looking up your result, the product, we are able to know that's working as a base or acid too. So let's go for another example, which is ammonia gas that's reacting with the water. Remember that ammonia was one of the main the limitation in Arrhenius. Arrhenius couldn't explain why ammonia is working as a base. Okay, it shows that some basic characteristics, but why using his definition, it wasn't. This could not be explained at the time. So, adopting the Bronsted-Lowry's definitions there, if we take this ammonia is your proton acceptor, which is known as base, according to Bronsted-Lowry definitions. H2O is now working as proton donor, which means H2O is now ready to release the hydrogen ion. So what that will become is H2O becomes to H plus and split into the OH minus like that. Does it make sense? Okay. Now, this water is now ready to release the hydrogen ion, to donate hydrogen ion to the ammonia. So what it becomes to is we get the ammonium NH4 plus aqueous ammonium ion and leaving that hydroxide ion like this. So having the hydroxide ion, this actually follows the definition of the Arrhenius. They're saying they release the hydrogen ion, hydroxide ion in the water. But this can only be explained by Bronsted-Lowry because we're using that water, the ammonia is working as a proton acceptor. Does it make sense to all? Okay. It's quite similar to sodium hydroxide, the aqueous, which is split into sodium and the hydroxide. This is kind of different too. This is something that can be explained by both of the Arrhenius and Bronsted-Lowry. Because according to Arrhenius, it's a hydroxide, there's a hydroxide ion release from the water. So it does sodium hydroxide, release the hydroxide. Okay, but this can also be explained by the Bronsted-Lowry too. When this high sodium hydroxide comes along to water, this is working as a proton acceptor. All right, so let's go for some more examples. The next page, not the 17, page 18. B. Shall we do it from A? Let's do it from A. Sorry. A. Considering the reaction between hydrochloric acid and sodium hydroxide, explain the neutralization reaction using Bronsted-Lowry definitions. Pretty easy. Okay. Again, you need to know what other products are simply by knowing the reactants we have. We have hydrochloric acid, HCl, aqueous, reacting with the sodium hydroxide base, acid and base reaction, neutralization, producing sodium chloride and the water. Okay, what we have to figure out here is we need to figure out which is your proton donor and proton acceptor. Don't worry about like why they want to donate the hydrogen ions and why they want to accept the hydrogen ions. We're not going to talk about that. That's actually organic chemistry related. It's more in the university chemistry. But now, just try to understand, memorize it as, oh, acid is proton donor, base is proton acceptor. Then what you just need to do is, this is your acid, and this is your base. That is proton donor, and this is a proton acceptor. Okay, see what happens. Yes? NaCl, because we mix them with the solutions. And how do we know the sodium chloride is aqueous? SNAP. SNAP. What are the SNAP? Sodium, nitrate, ammonium, acetate, phosphate. Potassium. They always come in the aqueous too. This is how we use the solubility rules again to figure out the state too. Okay. If you have something like silver chloride, okay, this is why you need to use the formula sheet, the cheat sheet. If you have something in the chemical in the compounds in there, more likely comes in solid. Okay. So this is a proton donor, this is proton acceptor, means this is ready to donate the hydrogen ion, so that what happens is hydrochloric acid is divided into these two. Out of that, guys, I want you to imagine, understand what I mean by aqueous. We did that in solubility. Aqueous means that the sodium inside of this is surrounded by the water. We called it hydrated salt before. Means it's been already surrounded by oxygens of the water, so they were separated prior to the reaction. Does it make sense? Okay, that's the standard. What do you mean by the standard for the aqueous? Something that's very different to the solid. Solid means that they're coming in that lattice structures, kind of joined together. When we say aqueous, they've been separated, means they're free to be reacted. They're free to accepting something. This sodium is now free, or likely connected to the chloride. So this is why they're forming the sodium, and this will form the sodium chloride straight away. Even for the aqueous state, this has been surrounded by the hydrogens. Remember this, the hydrated salt. Okay, salt has an ionic compound, by the way. I'm not talking about just your table salt in this case. What about in here? That means we have some hydroxides available, or hydrogens available. As this is a proton donor, this will be donated to the hydroxide, forming what? The water itself. This is how we explain the neutralization reaction using the Bronsted-Lowry definitions. Pretty simple. If you understand, oh, yeah, acid is proton donor. They want to donate the hydrogen ion, or they just want to get rid of the hydrogen ion. But important thing is, I'm talking about ion that's positively charged. When something losing positive, it becomes to negative. Just like over here, when hydrochloric acid lost the hydrogen ion, it becomes to negatively charged, leaving the negatively charged. When something gained the positive, it becomes to neutralize it or making the positive as well too. That makes sense, okay? That's for A, for Bronsted-Lowry definitions then. What about B? Could you try for B, please? Hydrogen chloride gas, and ammonia reacts to form ammonium chloride solid. That is also known as the acid and base reaction neutralization, even though it doesn't form the water. Remember that you have to put a state correctly in the Lewis diagram. It's been a while, so give it a go. So hydrochloric, it's not a hydrochloric acid because we don't have the solution form. We call the hydrochloride gas. That's basically comes in the gaseous state of the hydrochloric acid or the hydrochloride in this case. Ammonia generally comes out in gaseous state, so we can all like in an aqueous state. In this case, it'll be more like the solution aqueous. Okay, or you can write in the gases. It doesn't really matter for that state of the ammonia yet. But it's more important that they are reacting each other, forming something known as ammonium chloride, which is NH4Cl solid straight away. Okay, now what is important in here is that you need to think about what type of the bondings they have. Obviously, they are forming covalent bondings, except this one. Okay, so let's say HCl, when you're doing the Lewis structure, it's not a Lewis dot, by the way. So Lewis structure means you are able to show that covalent bonding in the lines. That simply means H and Cl with these some remainder electrons like that. That's Lewis structure of the hydrochloric acid or hydrochloride. This is reacting with ammonia. That's having 3 bonds with the 3 hydrogens, leaving the 1 electron on the top in the lone pair. Okay, hydrogen does not have any free electron because it only has 1. It lost 1 now. So what happened here is when these two are reacting each other, this is how something happened. Chloride, which has the highly electronegative, it will hog the electron from the hydrogen. So it becomes 2 hydrogen ion as it lost 1, and also becomes 2 chloride ions. The way we show that is show the full valence shell of the chloride with the 1 dot, 1 from the hydrogen, goes like this. That nitrogen is now ready to, and this is ready to hug that free hydrogen ion. So this is what it becomes to. This becomes the first NH4. Combine that with the positively charged on the top. Okay, remember the NH4, ammonium plus. Okay, plus that 2, combined with the chloride ion, which has remained, the minus. And the bonding between the positive and negative is known as the ionic bonding. Positive and negative is always with ionic bondings in this case, okay? Even though this is not a metal, I kind of explained to you before that ammonium is a very special type of the polyatomic cation that we can have. Okay, that's something we can, well, I don't expect to get questions like this, but it's good revision that how to draw the Lewis structures. Sometimes it's better to understand what is going on in terms of the electron sharing. Okay, now, according to Bronsted-Lowry then, we must say this HCl is working as an acid. Ammonia is working as a base. What is acid again? H plus donor. What's the base again? H plus acceptor. So what you get as a result of those is the base is receiving that hydrogen ion from the acid, becomes to ammonium ion, forming that into the ammonium chloride. So what you have to figure out here is, unlike the previous the reaction between hydrochloric acid to the sodium hydroxide that's forming the salt in the water, it does not produce any water. Can you spot the difference between here? But I still call that these two are the same, kind of the same, like a neutralization, because we have a reaction between acid and base. So hydrochloric acid and sodium hydroxide can also be explained using the Arrhenius experiment, Arrhenius definitions. That is producing some, it's releasing some hydrogen ion and hydroxide ion forming the water. But this, when the Arrhenius showed that experiment, okay, still be some exchanging that, losing the alkalinity and some of the acidity. He could not explain why this is working as an acid and base reaction, because the limitation of that Arrhenius definitions. But using the Bronsted-Lowry, we can explain many of those different types of the acid and base. So this is the things that you need to understand. Yes, acid and base neutralization produce salt in the water, okay, but they could be only be limited, some limited cases too. That's only when we have aqueous state according to Arrhenius definitions too, okay? So type of question you can get is something look like this. See, compare your answer in A and B and comment on any key differences that you noticed. One key difference. This reaction does not produce the water. Okay, it only has salt. But that salt is not metal and non-metal. It's basically salt. Okay. Second difference here. This second reaction also involves in some gaseous states. But as I said, both of the reaction A and B is known as an acid and base reaction, according to Bronsted-Lowry. And Arrhenius could not explain the reason why this reaction and the reaction B is the acid and base reaction. Does it quite make sense now? Okay, this is why we need to develop the theories and some of the some ideas so that we have a better ideas and better some explanation about some known experimental data. Yep. Just the differences for now, but you can just comment on that. This is the why we use in Bronsted-Lowry lots in our chemistry now. Okay, due to that limitation of the Arrhenius definitions. So on the next page, it gives you a good summary of the Arrhenius and Bronsted-Lowry. Okay, could you write it down, some acid and some missing point of that? It's pretty simple. And please highlight the Bronsted-Lowry limitation here too. That's the thing we had once in trial exam asking you that what's the limitation of Bronsted-Lowry. It's commonly you get questions like in the trials as well too. You get questions like compare and contrast the Arrhenius to the Bronsted-Lowry using an example. Okay, according to Arrhenius, acids are defined as acids. Let's follow the definition we're giving the base part two as ionized. Ions all dissociate and produce the hydrogen ions. It's important to you get familiar with this terminology here. Ionize or dissociate means they're kind of reacting, or ionize means producing the ions. So you got to use it quite a lot when you're talking about Ka value later on. Limitation to Arrhenius. Limitation is it's only limited. Yep, in aqueous state, which means on the solution to the solutions. It was maybe some solids, maybe, but it was kind of it couldn't explain the gaseous state, like working as an acid and base either. Okay, and some of those are not really write it down. Some of the base are not producing or containing the hydroxide ion. Like ammonia, for example. It does not have any hydroxide, but still release the hydroxide ions when you mix with the water. So it's quite thoughtful limitation. Bernoulli defined the acid as acid of proton donor, base is proton acceptor. Accepting the protons, and limitation is something that's very important for the Bernoulli too. To be classed as an acid, substance must have the proton hydrogen to lose. Does not explain the reaction between acetic oxide and basic oxide. Some cobalt oxide, for example, is something that he could not explain because they do not have the hydrogen at all, but still change the colors of the indicator. So like, okay, well, but it doesn't have the hydrogen. Like, how does the? So they kind of left as a limitation. So to develop that again, we're evolving into the new definition of acid and base, which we're not going to talk about today. Yeah, don't worry about it. Okay, just memorize it as the limitation for now. Okay, we will have a probably more chance to talk about limitations of the Bernoulli and Arrhenius. As I'm giving you some trial and HSC past papers questions too, you will see that what type of question you will get. And basically, guys, I know I explained quite a lot of the definitions today, but type of question, I'm just giving you a type of question you can get. It's only get questions about comparing contrast of the Arrhenius and the Bernoulli. You won't get many questions about Davy or Lavoisier either. Okay, this is the topic or like the contents that you can study like a day before, the night before the exam, and memorize it. Okay, don't just try to yourself like to memorize everything. If you can do that, that's fine. You don't have to worry about it. But it's quite straightforward. Some historical background required too. Then it's more important then, why do we use those Bernoulli's theory a lot? Okay. Some advantages with Bernoulli is something that you must understand. And after this 1.5, we're going to have a break. Okay. So let's bring it out. Again, some acid and base reactions. So HCl aqueous reacting with the water, H2O, the liquid, producing the H3O plus, aqueous and chloride ion. So I want you to just keep remember that acid is proton donor, base is proton acceptor. So how do we know proton donor and acceptor? We are looking up the product, see that which donates the hydrogen, which accepted hydrogen. So from these two, even though like you didn't know the hydrochloric acid is the acid, okay, you see that the product side there, it is the H3O plus from H2O. So it's kind of clear that the water accepted that hydrogen ion. This is how we define the base. This is working as the base. Okay, this means hydrochloric acid was working as an acid before. Now I want you to think about a situation in here that after they two, one acid and base reacted, it produced the hydronium ion. Now, in the states of the hydronium ion, Haley, do you think the hydronium H3O plus were willing to donate or accept the hydrogen ion further? Willing to donate. I mean, you can't accept it further more because it's fully saturated. It doesn't have any room to accept more. So only task it needs to do is it wants to lose the hydrogen as more. So I call that, this is working as now acid. More likely because it is willing to donate the hydrogen ion, according to Bernoulli definition again. What about chloride? Does chloride have any further hydrogen to lose? No, it means that it only can accept the hydrogen ion. So it will now working as some sort of base on this side over here. But what you need to see there is the relationship between the reactant to the product here. That something that becomes the acid before now becomes to remain as the base. Something that worked as a base in the reactant side now working as an acid on the product side. And what you see there is you only see that one hydrogen differences. Can you see that? Okay, there's only one from the hydrochloric acid HCl to Cl minus. There's only one hydrogen ion difference. From H2O to H3O plus, there's one hydrogen difference. Okay, so when we have a pair of the acid and base with a hydrogen ion difference, We call that as something known as conjugate acid and base pair. Okay, it simply means conjugate simply means that you have a difference of the one hydrogen, or literally it means that next to, is right next to. So for this reaction specifically, we have two pairs of the conjugate acid and base, which is we have hydrochloric acid that was working as an acid, now chloride ion that's working as a base. Okay, we also have hydronium ion that's working as an acid, also H2O that's working as a base. Okay, so in each of the neutralization reaction, we may get up to two pairs of the conjugate acid and base pairs like this. What about the next one? We have the same similar experiment. Sorry, the reaction. This time, ammonia, aqueous react with the water. Was it gas? Aqueous doesn't matter. Okay, that forms the, as we learned, this is working as a base, so it becomes 2 NH4 plus aqueous, and then leaving that OH minus aqueous like this. So what you see there here is the ammonia was working as a base. That's accepting the hydrogen ion. But ammonium is more likely working as an acid. So these two are related. These are connected. H2O here is working as an acid this time, but becomes the base of the hydroxide ion. So these two are related. So in this case, the conjugate acid pair, we have two pairs of the conjugate acid. One is that acid NH4 aqueous acid and base, NH3 acid and base pair. This is a conjugate acid and one pair. Two is we have H2O liquid acid and OH minus aqueous like this. Does it make sense? Okay, this is what we mean by the conjugate acid and pair. And the reason why we need to study about the conjugate acid and base is something later on we're going to talk about something known as a buffer. And to understand the buffer solution, you need to know about the conjugate acid and base pair a lot. That simply means that they have a difference of the one hydrogen. That's it. So if we have sulfuric acid, H2SO4, this is what? Acid. What would be the conjugate base of this? Conjugate base of this. Remember that even though it has two hydrogen in it here, when we said conjugate, it has only one difference of the hydrogen. So it would be HSO4 minus aqueous. This will be the conjugate base of it. But HSO4 is something that's very special. Okay, now if this is working as an acid, it can lose further up to one more of the hydrogen. So it now becomes the sulfate. Does it make sense? But can you see that? HSO4 minus is a state of the where it can receive the extra hydrogen too, because there's room for the hydrogen that it used to have before. Does it make sense though? Means that it can working as a base when it received the hydrogen ion from somewhere else, becomes to H2SO4 again. So in this kind of property that they are a substance that working as an acid and base together, we call them as amphiprotic. It's on the next page, or page 22. So we call this amphiprotic. The easiest way to remember there is, I hope you understand like what it means, like amphibians, frogs, in other words. Okay, amphibians, they can live under the water. They can survive under the water. They can on the ground. They can live under both different situations. Okay, so amphi stands for two, like a duality. So amphiprotic means that this is called the. Do we have a definition given here? Okay, the substance can either donate and accept the protons. It's known as the amphiprotic substances. For example, HSO4, hydrogen sulfate, is known as the amphiprotic because it can accept, it can donate the hydrogen ion. Okay, we have many of these, but water is something that's very important to understand. Water is, as you can see, this time here, water was working as a base because it's working as a proton acceptor. But that time, with the ammonia, the water was working as an acid. Means that water can also be an amphiprotic. It is an amphiprotic substance too, because it can accept Also, it can donate the hydrogen ion in the same time. Maybe the same time, maybe in different times. Okay, so one thing that it's good to memorize, I'm going to come back to this when we talk about pH today. Then when we have two waters, copy that down onto some given space over here, please. H2O, when we have a water to another water, I'll write it down in the different colors, okay? Because water is amphiprotic, means that it can donate and accept the hydrogen ions. Assume that if this is working, black is working as an acid, doesn't really matter for the water there, but assume that this is working as an acid if this is working as a base. Means that this will donate the hydrogen ion, this will accept the hydrogen ion. So we're leaving that 2. This black will now becomes 2 OH minus because it donated. This H2O in blue will becomes the hydronium ion, like this. Now, one thing about that is, this is something that very unstable form, means that they're ready to get donated again too, because they have some conjugate acid and base pair. So this reaction is reversible. Why am I talking about this? Because you got to find the K value of it. That's product of the reactants later on. And this is something we starting learning about, something known as pH and pOH, further up to the pKa and Ka values. But that will be something covered in the last minutes of today's class. pOH, pH. It's quite interesting that how we define the pH. It doesn't mean that you can use that when you're measuring the pH of your swimming pool. Okay, let's do a couple of questions before we move on, before we have a break. Page 21, please. We're going to move that together. So identify the conjugate bases for the following acid. Remember that conjugate base means it has one less hydrogen. So if this is acid pair, 1 HNO3 is an acid, the conjugate base would be NO3 minus. Simple as that. Okay. 2, if you have water that's working as an acid this time, this means OH minus, one less hydrogen ion, would be your conjugate base. 3, H3O plus working as an acid, obviously, then H2O is your conjugate base. 4, H2SO4 working as an acid, this means HSO4 minus is your conjugate base. Easy as that. Okay, next one, OH minus is now working as a base. Remember that conjugate means having one hydrogen ion differences only. So adding that to hydrogen ion, because it's working as a base, means we get the H2O. Easy. H2O is now working as a base. That means H3O plus must be the conjugate acid of the H2O. What else we have? We have the HCO3, hydrogen carbonate. Now, conjugate acid of that, it means adding that hydrogen ion in it, so it becomes H2CO3. Okay, 4, we have SO4 minus working as a base. That's adding the, I'm accepting one hydrogen only, HSO4 minus. Don't write the H2SO4, by the way, because conjugate always means one hydrogen ion differences too. That's not, when you say H2SO4, that's not a conjugate anymore. Does it make sense? Okay. Okay. Sorry, I just need to finish this. So in chemistry, like when we're talking about the acid, we're using the different terms called the monoprotic, diprotic, triprotic. It's very simple. Monoprotic simply means one proton release. Okay, it's very simple. Mono, one, protic, proton, acid, release. That's it. So example of those is hydrochloric acid, fluoric acid, nitric acid, acetic acid. They only have one hydrogen available, so they can only donate one. It's very simple as that. Diprotic means they can donate up to 2 because they have a 2 in excess hydrogen ions. Sulfuric acid, carbonic acid, for example, like they are the diprotic. It's just a bit of a terminology you need to understand. You don't have to memorize it because you see that mono, di, tri means stands for 1, 2, and 3. Protic means protons only. Triprotic is something very interesting. They can donate up to 3. Now, we had a trial question at HSC that, remember that we talked about the citric acid? Okay, citric acid is known as a triprotic. The reason why you need to know that triprotic and diprotic is because depends on how many hydrogen ions they have, the reaction ratio would be different. For example, triprotic acid plus sodium hydroxide. Because we have 3 hydrogen ions left in that triprotic, we need to have 3 sodium hydroxide to balance the chemical reactions. We're going to talk more about the balancing and some calculation involving the chemical acid and base reaction after the break. But don't miss that, because I saw that when I was marking some of the trial past paper. People misread or didn't kind of ignore. Okay, they're saying, "Oh, I didn't read that." I don't know why. That's what they said. I didn't read that. I'm like, you didn't read the question, and they missed out the triprotic and they balanced it wrong. It was a 5 marker. They only got a 1 because they started wrong from the balancing equation. I can't give you further mark. Yes, there'll be some carried on error, but if you're unlucky, if you're meeting some really strict examiner marker, they won't give you any mark for that because you misread the question. Okay, don't miss that in the school exam or the trials in the HSC. Okay, I show you one question and let's go to break after this. Okay, so 1.13, please. Write on equations to show each of the following acting as an acid and base with the water. Now, let's see that whether that's working as an acid and the property of those two. All of those you're given are working as an acid and base, which is called that amphiprotics. So when we have to show the 2 equations for each. When HCO3 is working as an acid with the water. Again, remember that this means that this is working a proton donor. It will lose proton. So it becomes 2 H3O plus aqueous and CO3 2 minus aqueous when this is working as an acid. But when the HCO3 minus is working as a base, then this will becomes 2 when the reacting with the water. This will accept the hydrogen from the water. That becomes 2 H2CO3 acetic acid, and then leaving that hydroxide ion like this. Same for the next one, B HPO4 2 minus reacting with the water. Now this is now working as an acid, releasing the hydrogen ion becomes 2 H3O plus hydronium ion and leaving that PO4 3 minus phosphate ion leaving behind. HPO4 2 minus now working as an acid with the water. Then it becomes 2. Sorry, now working as a base, I should say. In H2PO4 minus and leaving the hydroxide ion. HSO4 2 minus working as an acid means leaving the H3O plus aqueous and having the SO4 2 minus. And if that's working as a base, then it becomes 2 H2 SO4. Sorry, that should be a minus and minus. Become SO4 and OH minus aqueous will be formed. But lastly, when the water, show you that before, when the water is working with reacting with the water, it will be in the equilibrium, the reversible reaction that forms the hydronium ion and hydroxide ion together. Okay, this is why we need to understand about Bronsted-Lowry, proton acceptor, proton donor. Well, once you get it, this is pretty straightforward. Conjugate, don't just forget about conjugate acid and base pair. You may get one like a multiple choice related to the conjugate acid and base. It's quite common that we get it in school exams. Any questions up to here? Okay, shall we have a break? All right. Page 61, chapter 2, please. Let's do a quick revision on some module 2, calculating some moles and volumes. Okay, could you try for exercise 2.1, please, now? This is the question that you're going to deal with a lot. Page 61, yeah. Exercise 2.1, please.
That was really scary. Okay.
Hmm?
Alright. So you saw me getting abused, right?
I saw you getting abused every week, though,
Yeah,
so I'm not so surprised
Since
about
you
it.
lied.
Yeah.
What? What's so ugly? But that's just a nice one. She's just touching me. It doesn't have to be. I don't think it matters. It doesn't matter because I'm being with shush. You asked me a question. Oh. That's my camera. Look, she went. Girl. Are you okay?
You're disgusting.
I didn't say anything. What's that? Why'd you get rid of it? We're doing the same one.
Stupid. Oh, I should put John was on my background.
Me too. I showed my dad and he said he actually thinks it looks like him. What the fuck?
Yeah,
What?
exactly. She's just
You can't say anything. No, Rachel can say something, but Haley can't say anything.
Say something.
Can I help you choose?
너가 누군데? 네가 뭔데?
나?
아니야. 아니야.
No.
Yes. Stop.
Finished?
I'm not racist. Oh, yes, we
Yes, sir, we are.
Oh, good.
Unless it's hard.
Oh, it's like
It's been a while. You're dealing with some stoichiometry questions, and well, I probably warned you, like when you state module 2, that you get lots of those in year 12, and this is just pretty much knowledge that you need how to balance the chemical equation with the states and write it down the relevant equations, formulas, templates. So what I'm going to do right in here is I give you some sort of like a template that you can follow every single time dealing with the stoichiometry questions. The one is you always start with the balanced chemical equations. This is something that's very important because we have to figure out the reaction ratio between the reactants and products, or in between the reactants and reactants. Write it down in the state, the given states if you're known. So you know the state of the solution is always be aqueous. So what we're given here is barium hydroxide, OH2 aqueous, as a reacting with the solution of nitric acid. So I ask you to memorize it. This is the only way you can do this question. Okay, and then once these two are reacting, then they produce, remember that, acid and metal hydroxide produce salt and the water. That's how you use a template. So salt is basically barium, nitrate is produced, and nitrate means night in the snap, so this must be aqueous state, and H2O comes in the liquid. Once you get that, balance that, we require 2 of the nitric acid and producing 2 of the water like that. That's always your primal step you need to do with the balanced chemical equations or stoichiometric questions. And then write it down, all the relevant information. Write or summarize it if you need to. So what you have given here is you're given some, let's start from here, and we have given 150 mils of the nitric acid. So volume of the nitric acid, HNO3, is given as 150 milliliter. Now, don't leave your unit into milliliters because we don't use that in calculation. We have to convert it into the liter form with the sig fix given. Concentration of the HNO3 is also given as 0.15 mole per liter. And you're also given the concentration of the barium hydroxide is 0.20 mole per liter. So up to here is, I call this kind of prep work of the chemistry like some calculation involving chemistry. It doesn't mean like you get a mark because you've done all the information here, but you may lose a mark if you don't write them, some of those informations. So keep that in your mind. You need to write all the relevant informations, especially in chemistry. Yes, chemistry teaches the pickiest, and we mark it really harsh on your calculations, as we got to deal with lots of calculation questions. Once you got it up to that, you got to think about here that we are given some volume of that and concentration of that. The question's asking you, hey, how much of those barium hydroxide is required to fully neutralize the nitric acid? So you need to find the number of moles, more likely. You can find the N, number of mole of the nitric acid, for the relevant with adding like some formulas. You can either use N equals to M over MM, CV, or even for the gases too. I hope you remember that. PV equals to NRT, or even some molar volumes too. Yeah, this comes along. They won't tell you which one you have to use. You need to figure it out. Oh, you got the solution. That means we have to use N equals to CV. The N equals to CV comes like this, 0.15. That times that 0.15 gives you 0.075, if I'm correct. Let's check it again. 0.025. Losing 225 mole of the nitric acid is now given. This is the amount of the moles you're given. Then you got to think about the reaction ratio between the nitric acid to the barium hydroxide, which is 1 to 2. This means that for 1 barium hydroxide, we need to have 2 nitric acid. So according to the reaction, sometimes known as molar ratio of barium hydroxide to nitric acid, which is what? 1 to 2. Can I continue on here? And of the barium hydroxide is therefore half of the N of the nitric acid. If you're not too sure how to determine the ratio here, I would like to solve that actually in some ratio forms too. Or think about it as for 1, we need to have a 2. Means if I have a 1, I need to have a half of that. Okay, this is something that you have to think of here. So for that, 1 mole is basically 2. That's what I meant. Make sense? Okay. Then if I have, so think about it here. If I have 1 mole, I need to have half of that. If I have, yes, I was right. Okay, means that no. Are we given nitric acid? Okay. It'll be half. I was right. Okay. My bad. So it means that you get the half of the 0.0225. So 0.0225 divided by answer divided by 2, you get 0.1125 mole. This is the amount of the barium hydroxide required to fully react with the given amount of the nitric acid. Then, are we done yet? No, we need to find that into the volume. Remember that C is equals to N over V, means that we can find the volume by N over C here like this. This means volume of the nitric acid is therefore N. Sorry, not the, sorry, why I keep saying nitric acid? Volume of the barium hydroxide is 0.01125. That divided by given concentration 0.2. That divided by 0.2, you get 0.05625. And then finally, matching that to the given sigfic values. If you're given 2 sigfics in your answer, in your questions, or if you use the annual 2 sigfic in your calculations, you need to follow the sigfic of 2, that is 0.056 liter into sigfic. This is the final mark. And guess what? If you have that question in your school exam in year 12, there will only be like 2 or 3 marks. And you'll lose a mark if you're not showing any of this working out in your answer. Okay, including the sigfics and the calculation too. Okay, so that's what we have done in year 12. The new thing is probably memorizing the template, but as I said, the pre-USHM knowledge in year 12, in year 11 and 12. Okay, what about next one? Try for the next one using the same template that I provided here. I know some of you are not kind of familiar with those templates, but this is the A to Z of the stoichiometric questions. Give you 3 more minutes. When you're writing all the relevant information, make sure you include that suffix given in your questions too. So that's how we can just save your time in the exam later on too. So we need to figure out how many suffix you have, whether they are used involved in the calculations. So even though you have given some suffix here, but that is not involved in the calculations, means you need to follow something different, some other suffix values. What I mean is, you're given 3 suffix and sometimes 2 suffix, but if you didn't use a 3 suffix in your calculations, you need to follow the 2 suffix that's involved in the calculations. Okay, maybe a 2 and 3, but at the same time. All right, and sulfuric acid given as 0.00500 mole per liter, and the volume of that is given as 75.0 milliliter. That's 0.075 liter. That. Okay, always use that the formula to find the number of moles. You have a various method. N equals to M over MM, N equals to CV, N equals to using the PV equals to nRT for the gaseous state. You never know. Yes, don't expect like you won't get any of the gaseous state. You can. Okay, and I hope you remember that at 25 degrees Celsius, we have an exact volume of the 24.79 liter volume. So that's something you also need to referring to. That's what I mean. Like, yes, you get the year 11 content in the HSC a lot nowadays. So find the N equals to CV. So specify what number of moles you're finding for. You're finding for the sulfuric acid number of moles. That's a CV. That is 0.005 times 0.075. And you get 0.005 times 0.075. You get 0.000375 number of moles. Okay. Now, according to the reaction ratio between barium hydroxide and sulfuric acid, according to the reaction ratio, we can simply say N of the barium hydroxide is exactly the same as sulfuric acid. Therefore, using that C, if you're not too sure about how to find the volume, it's good to write it down C equals N over V first of all, and convert it into therefore V equals to N over C like this. Okay, I don't mind to see that. It's actually a good method. So you can minimize and make any silly mistakes. So volume of the barium hydroxide is therefore is N over V, that we have 0.000375 divided by the concentration given 0.1. So that gives you 0.00375 liter. Now check this suffix. We have 3 suffix given, so I'm gonna follow the 3 suffix, which is 375 liter in 3 suffix. Okay, nothing really special about these kind of stoichiometry questions, because I assume that you did that a lot in year 11. It's a stoichiometry type, and there's one thing you have to be aware is the products, but that's also be some sort of pre-assumed knowledge. Let's move on to year 12 level. Next page. As I said, let's talk about the enthalpy again. Yes, Haley, I know your favorite. Since when? Okay. Hannah, what is enthalpy? Well, we talked about enthalpy lots in module 4, and I warned you that you'll get the enthalpy questions again in module 5 too. What is enthalpy? Yeah, what is delta H referring to? Okay, so you have to figure out the difference between enthalpy. Oh, by the way, this year HSC, you will get an enthalpy entropy Gibbs free energy in HSC. That's 100%. So be wise. I mean, study that. You know what's coming in the exam. If you don't study for that, if you ignore that, you lose good 4 to 5 marks in the HSC. That's like 4 to 5% of the whole HSC marks, by the way. Okay, study that. And I'll try to explain you as we go to enthalpy entropy. I'm going to go through some trial papers later on too. But enthalpy is simply known as I hope you remember that, the heat content. Or if that's too hard to understand, I describe that as some sort of the chemical potential energy. Do you remember that? Like we talked about, hey, the energy difference between store in the reactant side, energy stored in the product side. So what we have is difference between the energy difference between reactant and products. Energy can be released, energy can be absorbed too. So enthalpy or delta H is not an enthalpy. It's actually known as change in enthalpy. Think about what I mean by the change in. Change in means that final enthalpy minus final initial enthalpy. So final as in like a enthalpy of the products, H of the product minus H of the reactant. That's what I meant by delta H. And we learned that when the delta H is less than 0, the heat must be, okay, think about it in this case here. Meaning of the delta H is less than 0 means that we have a greater amount of the energy on the reactant side than the product side. Okay, means that the energy must be released in forms of the heat. We call that exothermic reaction. When the delta H is greater than 0, we call it endothermic. Rachel, give me one example of the exothermic reaction then. Yeah, thank you. Combustion is one type of the exothermic. It always releases the heat when you're burning the fuels. Okay, then Haley, give me one example of the endothermic. Photosynthesis isn't required the heat absorb that too. So you can think of like the products that produce from photosynthesis, which is carbohydrate and the oxygen. It's much more creating the greater amount of energy than the reactant side. Okay. This is kind of brief summary and a revision on the enthalpy. But why am I bringing this one in again too? Because we are going to talk about something known as the enthalpy of the neutralization. Okay. Now, one thing that you have to understand is delta is written as delta H NEUT, neut or neutralization. Is a very special type of the change in enthalpy, just like a combustion. We learned that delta H combustion is always be negative because it always be exothermic reaction. The neutralization reaction or delta H neut is more likely generally be negative as well too, which means it will release the heat. Then what would be the consequences of this system release the heat if we have a water? If the heat is released, think about the combustion, heat is released and the water receives that, what happens to the water temperature? It rises too. So the clear sign of the exothermic reaction is we will see that we can feel, sense the heat. Okay? So think about combustion of the fuel, we can sense the heat. This is why we're burning something to produce the heat. Okay? Which means in every single time we have an acid and base neutralization, technically, you should be able to sense the heat as well too, if you have a certain amount, a huge amount. It means you will detect some change in the temperature of the water or the mixture as well too. Does it make sense? Okay. And things that you have to remember is the delta H is founded by Q on the N, where the Q is amount of heat or the energy. That could be produced, could be absorbed. So I will just leave that a Q for now, divided by number of moles. This is a general formula for the delta H, but when we're talking about delta H of the neutralization, remember that I'm going to put the minus Q on N because we just say that delta H of the neutralization is negative. This is why we put the negative value here. Same for the heat of combustion. I go put that negative because we know that heat is released in exothermic. We can't do the same thing for the endothermic. We must put in the positive in this case. Now, Q in the neutralization means basically the heat from that neutralization reaction, the total amount of heat divided by, now, N is something that's very important, the number of the H2O produced. Then let us think about why that's something that's very important. So bring back the acid and the base reaction in terms of the aqueous, rather using the Burns and Laurie or Arrhenius, you always know that they'll produce a salt and the water. Okay, now how do you know they reached at the neutralization? Considering that the acid is lower than having lower pH than 7. Base has higher pH than 7. When you're mixing them two, you're basically looking for somewhere like a pH of 7. And remember that pH 7 is referring that water presence to. Means as a product of the neutralization is the water, the amount of the water, amount of the H2O produced is basically same as the amount of the neutralization occurred. Does it make sense? Think about what I mean by neutralizing it. We don't want to get any of the acid nor the base, so we want to get it neutralized as in that forms of water. And this is why we only take the number of mole of the water, not the number of mole of the acid nor the base. Does it make sense to all? Please remember that this won't be given in your formula sheet. Does it? Maybe, maybe not. It won't explain you as much in detail as this. You okay, Duan? Hannah, you okay? Okay, can I move on? All right, then how do you find the Q? Hannah, how do you find the Q? MCAT. That's very good. Q equals to MCAT. Now, I'm going to leave that not as negative yet because Q is about the energy. We can't have the negative energy technically saying. So I'm going to just leave the Q equals MCAT, where generally speaking in the combustion, we learned that M is mass of the water. C was specific heat capacity of the water. Delta T was change in temperature. Now, let's talk about Q in the neutralizations. Okay, M is not the mass of the water anymore because we're mixing up the acid and base, which means you're making something salt water. Guys, salt water is something that's very different to the water. It won't have the same density as a water. It will be kind of heavier or something lighter. So mass of the, it means that mass of the mixture, sometimes known as salt water, maybe some remained acid and base. C is the specific heat of the capacity of the mixture. Okay, now delta T is change in the temperature of the mixture. Now remember that I'm keep using that mixture, not the something in the water, because we are mixing some acid and base, making some mixture of the salt and the water in this case. All right, now this is the thing. In the trials on the HSC, if you're given the very specific number of the M, saying that, hey, I have 100 mils of the sodium hydroxide. That's from the 2020 HSC paper, by the way. Okay, I have 100 mils of sodium hydroxide. Its mass is, however, 107.9. You need to follow that mass. Don't just make an assumption that, oh, we have a solution that will be same as the water mass. No. Okay. Each of the chemical solution would have a very different like a mass. If you think about alcohol, for example, even though you have 100 mils of the alcohol, they'll be lighter than actually 100 mils of water. Okay, so each of those have a very specific density. If you're given a density, if the density or the CR given, follow the specific or exact the numbers. Something that's very important for the exam. But this is something when you're given that. Okay? But in many cases, like a school practice times, we can't find that density value, we can't find specific capacity because we don't know the specific values. In that case, use assumption. In other cases. So what are the assumptions? It's given on your page, page 63, assumptions part over here, okay? Let's highlight that assumptions because you need to Okay, you don't need to memorize it, but you need to understand, and probably you need to utilize that. First assumption is the salt solution formed from the reaction has the same specific heat capacity of that of water. So we kind of assume that, oh, yes, we have a salt water, but the specific heat capacity is the same as the water, which is, do you remember that? 4.1 C is a C of the water, 4.18 times 10 to the power 3 joules per kilograms per Kelvin. Now, as we're talking about change in temperature, it doesn't really matter. The unit for the temperature is Kelvin or the degrees Celsius in this case. We deal the same because we're talking about change in the temperature. This is the specific heat capacity you're given in your formula sheet. I recommend to use the one in the formula sheet always because this is the thing that you minimize making some silly mistakes. Some textbook I know that they're using a different unit. So for that, I should probably just quickly write in here. See if C is given at 4.18 times 10 to the power 3 joules per kilograms per Kelvin. This is same as 4.18 times 10 to the power 3 kilojoules per grams per Kelvin in terms of unit. Okay, and sometimes some textbook just giving you 4.18, that is joules per grams per Kelvin too, okay? But this is something that's very confusing new because we have a different type of units given over here. So this is my recommendations, my personal recommendations. I would like you to follow whatever the value you're given in your formula sheet because you will get the formula sheet every single time. This is the standard for units that we have in your formula sheet. And you just need to follow the units to convert the units to matching up the values. This is something that's very important in enthalpy calculations. Remember that. I guarantee many of you will get it wrong at least once in your life in this HSC preparation because of the unit. There's something that's very easy to lose. Okay, easy to forget about. All right, that's a C. It's given here. It's given here. Don't worry. Okay. Second assumption that we make is that thermal energy released from the reaction in transfer salt solution is there's no energy loss. We do not consider about energy loss in this case, unless you're given, unless they're told, hey, only 10% of the energy got transferred. Okay, that's a kind of general assumption. Third, if the mass of salt solution form was not measured, it can be assumed that it has the same density of the water, which is 1 gram per 1 milliliter. Which means if I have a volume of 300 milliliter, we just take the density of the water, that'll be same as 300 grams in this case. Okay, and that's most like a water, and that's given. You can just put the negative value if you like to. Remember that the N of the H2O is something that's very important for the neutralization enthalpy because we are accounting for how much of the neutralization went through. The sign, the evidence of the neutralization is basically proven by amount of the water that's produced in this reaction. All right, let's do some questions related to that 2.3. You might need a bigger space than that, so I recommend you to use a different separate notes. Book 2.3. Let's do it. 50 mils of the diluted standard sodium hydroxide solution was added to neutralize 50 mils of the 2 molar solution of the ethanoic acid. The temperature of the mixture rose from 22 to 33.7 degrees Celsius. Determine the enthalpy of the neutralization. This is the kind of question you will get a lot, but the way you solve deal with the question is always same as a stoichiometry, other stoichiometry questions. So start with the balanced chemical equation always. That we have sodium hydroxide aqueous that's reacting with ethanoic acid. Ask you to remember that. That is CH3, CH3, COH, aqueous, producing that acid and base reaction, salt, sodium acetate, and the water. So you need to figure out that the reaction ratio between everything is 1 to 1 to 1 to 1. Okay? After you got that, write it down all the relevant information that you have again too. That is N Or you can just simply find that. Think about what the aim of this question. We want to find the delta H of the neutralization. To get that, we need to have the number of mole of the water. Okay, so I can skip some of the steps to save my time. What I do is the number of mole of the water is same as number of mole of the the acetic acid you added, according to the reaction ratio. Therefore, N of the CH3 COOH, or so simply the water. Let's write it down for now. CV, concentration that you're given, 2 mole times that. Now, converting 250 mils to milliliter always 0.05. That gives you 0.10 mole. Is that same as N of the H2O. Okay, the first step. Second step. Then we have to think about it in here. The mass. Assume that mass of the solution is from the volume of the mixture, that total volume of the everything. That, think about it here. We mixed 50 mils to 50 mils. So that would be 50 mils plus 50 mils, giving you 100 mils. That is therefore the volume is 100 mils. As we assume that it has the same density of the water, the mass of the solution is 100 grams. This is why we need to make the assumption. Otherwise, you can't figure out exact mass or the sum of the mass of the solution in this case. C, specific capacity, as we mentioned, an assumption too, it will be given as 4.18 times 10 to the power of 3 joules per kilograms per Kelvin. Now, if you're confident enough to convert it in unit, that if you want to go for the kilojoules straight away, you can do so. Okay, but if you're not that confident about like converting in unit, follow that. What I mean follow that is, you know that there's kilograms given to C. That means you need to convert the grams to the kilograms to matching up the unit. So this will now be 0.100 kg instead of the grams. Does it make sense to all? Okay. And then we can find the change in temperature by the final temperature minus the initial temperature. The final temperature was given at 33.7. Then minus initial temperature of the 22.0. This gives you that 11.7 degrees Celsius. As I said, as we are looking for the difference between temperature, it doesn't matter for the unit, for the degree, whether there's a degree Celsius or the Kelvin. That means you do not add up 273.15 to get the Kelvin, to convert it to Kelvin. Make sure you don't do that, because I see some cases like people actually do converting unit to Kelvin because of that. Does it make sense? Okay. So what we get from here, we can get the Q value. Q is then equals to MCAD. That's you have to put all the values in. 0.1 times that 4.18 times 10 to the power of 3. That times the 11.7. Then you get 4,890.6 joules. Make sure you're getting the joules now yet. Okay? I hope you remember that. Delta H, any of delta H has a unit, standard unit of the kilojoules per mole. Means that you need to convert it into the kilojoules by, divided it by 10 to the power of 1,000. That's simply 4.8906 kilojoules then. Okay, and that's what I mean by, yes, you can convert that joules in the C value prior to the converting that unit, but you can do that so. Does it make sense to all? Now, final stage, delta H of the neutralization. Make sure you show that all the relevant formulas you're going to use is equals to minus Q on N of the H2O. That is, we are minus 4.8906 kilojoules divided by the number of moles that we found on the top. That's 0.1. So that divided by 0.1, you get 48 minus 48.906. Now, follow the sig figs. You're given 3, 2, 2, and 3, and 3, and 2. Did we use the 2 moles? This here, 2 moles in your calculation. That means your lowest sig fig would be 2, not 3 anymore. If you didn't use that 2, you have to worry about the sig figs. But as we did that, you need to convert it into the 2 sig figs. That would be minus 49 kilojoules per mole. This is the final answer. In 2 sig fig with the correct unit of the delta H. Make sure you show the units of the delta H in kilojoules per mole. Does it make sense to all? Okay. Now, this is when we use the assumption, which means that this is not a real value, this is in the exact value, correct value. Because actually what happened is sodium carbonate water would not have the same density of the water. Okay, sodium carbonate water would not have the same specific capacity of the water too. But we don't know, you're not given anything. That means this is the time that you can use the assumption. This is the only time you can use the assumption. Does it make sense to all? Okay. All right. Try for 2.2, 2.4 then, please. I leave that working out so I can just refer to this working out again and again. Give you 2 more minutes. If you're not sure what to do, I really recommend you to follow the template for the chemical, like some template as in like go through the order by orders too, because this is probably the best way to. If you can comprehend why we need to do that, that'd be great. But if you're not, try to follow the template that I provided you. And yes, you need to memorize quite a lot for chemistry. So valencies, some type of the chemicals, some reaction results or products that again, if you got it wrong from the balance equations, I'm sorry, you have no chance. Okay, so barium hydroxide is reacting with the acetic acid, producing barium acetate and then some water. Neutralization again too. Everyone good up to here? Okay, then what we have to do is, from that given, we're given that ethanoic acid number of moles as well as volume. That is neutralized with the 25 mils of the barium hydroxide. So amount of the water will be determined by amount of the acetic acid you're given. That you can see that you have good reaction ratio. That's 2:2. So N of the H2O can simply say N of the acetic acid that you're provided, which is CV, can be found by given concentration 1.5. Make sure you convert the 50 milliliter to the liter. That's 0.05. Then that's 0.075. Let's check that again. 0.075 mole. So this, let's write it again. This is same as number of mole of the H2O. Okay, now the total mass of the solution is from the volume of the mixture. The total volume is 25 mils plus 25 milliliter gives you 50.0 milliliter. If you like to, you can convert that into the 50 grams. That's 50 milliliter, which is same as 50 grams. That's equivalent to, in kg, 0.05 kg. Sorry, 25 to 50, so 75, my bad. Misread that. 25 and 50 give you 75 milliliter. Assume that we have the same density of the water, that would be 75 gram. That's 0.075 kg then. Any questions up to this point? See, I just used your value given in your formula sheet. That's 4.18 times 10 to the power 3 joules per kilogram per Kelvin. And then find the delta T, which is the change in temperature from final 34.0 minus 21.3. You get 12.7 degrees Celsius or the Kelvin. Yep, then just put that in your formula. This is why I left the template in the black. I'm just still kind of filling up the numbers. That's all you need to do for this type of questions. Then Q equals to the MCAT that we have given 0.075 times the C, 4.18 times 10 to the power 3. That times that 12.7. This will give you times 4.18 times 10 to the power of the 3. That times that 227. Oh, 12.7, sorry. You get 3981.45 in joules. And make sure you convert that into the kilojoules. That is 3.98145 kilojoules then. I'd rather put the exact values during your calculation, because later on we're going to use that value to calculate the final values, and I don't want to get any sig fig errors in this case. So delta H newt can be found by the formula minus Q on N of the H is H2O. That's 3.98145 divided by given number mole, 0.075. That's giving you 53 minus 53.086. Okay, don't leave your numbers just like here. Finalize it. Show that what you're looking for, what you're finding for. You're looking for that delta H newt, which is same as minus. Checking the sig figs that you're given. You're given 2, 3, 2. So as U is a 2 sig figs, you must leave your answer in the 2 sig figs. The lower sig fig values that you have, that is 53 kilojoules per mole into sig figs. this is how you need to write for this type of the answer for this type of questions again too. All I can tell you is, guys, please follow the template or understand all the situation here. This is something that's a little bit different to the combustion, that we are not really putting that in acid and base into the boiling the water. Instead, we are looking for, I show you that. This is actually what you have in your final too. That's what we do in the prac too. We're using something called a calorimeter, or sometimes use a styrofoam cup. Put some acid and base in it. We measure the change in temperature. Okay, and what we always do is we try to put some excess amount of some acid and base so that make sure all that gets neutralized so that we can calculate them. Okay, that is the experimental setup for this neutralization of the enthalpy. Okay, now something that's very different to combustion. Yes, you may get the combustion enthalpy again too, but they're likely. I'll show you one question in 2020 HSC. That's what we had before in 2020. That's like now 4 years old. Before, yeah, I realized that too. It's 4 years. Now it's 2024. Yeah. Yeah. Well, now you can get the 2023 paper, and it's available in NESA and all that. But that's what we had. I'm not going to do that question. I just simply want to show you that. What I mean by you need to follow the exact value if you're given the exact value. The questions gave you, hey, we have the hydrochloric acid initially. The mass of this solution is 103 grams. Yep. You can't use the assumption that 100 mil is the same as 100 grams anymore because you're given 103. Why am I saying this? Because I saw so many students just ignore that and they say, oh, was it 103? I just made an assumption. I'm like, you're a stupid idiot. I really said, you stupid idiot. It's written down there. It was written. Please read. It's not that hard. Read and highlight it if you need to. Don't miss a single piece of the information because that's 5 marks. Guess what? They only got 1 out of 5. Do I have to be sorry for that? No. I mean, I feel really bad. I got to get that because it's a HSC paper, by the way. The last exam of the HSC 2020. Even that specific capacity given as 3.99 joules per gram per Kelvin. Okay, it wasn't 4.18. The person used 4.18 too. No chance. I can't, even if I try to give it a mark, no chance to get a mark from that too. Read the question very carefully, highlight it. Yes, guys, one thing, you can bring your highlighter into the exam. You can only highlight the questions. You can. Okay, use highlighter if you need to. Underline is fine, highlight it. That's better because you can check it up really easily. Your eye catches up the color really quickly. Okay, you don't have to read through the questions again. That's how you need to save your time because 5 marks in HSC, you only have 7 minutes to do this question. Can you do this question in 7 minutes? You got to think about yourself. Can you do this in 7 minutes? Maximum 8 to 9 minutes. Can you do it? Because you have a 3 hours exam, 100 marks, and you got to think about checking time as well too. So the way you can calculate the amount of time you need to spend for each of the HSC marks, 1 mark equivalent to 1.5 minutes. Means in every single multiple choice, which is 1 mark equivalent, you only have 1.5, 90 seconds. So it's a good idea that you have a timer with you, okay? Set a timer for 90 second marks, do that multiple choice. This is what I'm saying by, for 20 marks of the HSC in the multiple choice, you only have 30 minutes. You only have 30 minutes to do that. If you save your time there, you gotta save your time. I'm gonna talk more about exam skills and techniques you need to use in the when we're preparing for the HSC trials because that has the same format as the HSC, and you need to keep practicing that. This is why it's so important to do that exam in the exam settings. Anyways, this is the question about the neutralization, enthalpy of the neutralization. Any questions about this? Okay. You will get 1 in your topic test or 2. I'm going to move on to quite further. Page 67, please. This is related to some of the things we're going to do next week as well, but I'm going to introduce some more little more complicated than before. There's some calculations in acid and base. So for the stoichiometry type of questions, I really think this is the pre-Ocean knowledge from year 11. If you're not confident about it, make sure you practice in this holiday. This is the only time. You won't have a time to practice your stoichiometric skills in your school when the school term starts, because you got to get busy with your school assessments, by the way. Okay, you don't have a time. Now, you don't go to school, do you? You have plenty of time. Practice it now. This is the only holiday. Easter holiday, you have no time. You got to get to be working on some other assessment. The holiday after is a trial preparation. Holiday after is a HSC preparation. Guys, remember that. Should I write the D-Day for the trials and the HSC from under this board now? I did that for last year, since like February. I actually started from like a D300 for the HSC. Now it's almost a D300 for you. Yeah. I'm just giving you a reality check for the year 12, because it's something that's very different to year 11. Remember that you only have 300 days for your HSC, or less than 300 days. That's not a lot. Yeah. Okay, let's talk about some acid and base, like so how we define it quantitatively. This is page 67. Thank you. Okay. All right. I hope you still remember that the meaning of amphiprotic. We did like an hour ago. Okay, amphiprotic means it can working as an acid and base. It can working as a proton donor, proton acceptor. Yeah. So we talked about it. Water is the typical amphiprotic substance that it can working as H2O liquids. When these two are working each other, it's going to equilibrium. It comes back to the water stage, but it also forms the hydronium ion, H was, and the hydroxide ion like this. Okay, now, and one thing you also need to remember is the H3O plus the same as amount of the hydrogen ion released too. Okay, this formed same as this is like ionized. Okay, so we got to take the same concentration of the hydrogen ion to the hydronium ion in this case. All right, as you can see from here, you see this is in the reversible reaction, and this will reach to something we know as the equilibrium state. Let's talk about equilibrium again too. At the equilibrium, you won't see any change in the concentration. Okay, you won't see that, but because of that, there are constant rate of reaction forward and reverse reaction. That's what we learned. Okay, that means at the equilibrium, we may consider that we can find the K value of this. How to find the K value again? There's a product concentration on the reactant concentration. That's what we have in product concentration on the top in the numerator, and OH minus like this. But if you have a look at your reactant side, you have a liquid, which is the pure substances. We do not have the concentration for the pure liquid, pure solid. So I just leave that as this. This is the K value of this water at 25 degrees Celsius. Now, the reason why we have to figure out the temperature is greater the temperature would have slightly different K values. I hope you remember that temperature was the only factor that can alter the K value. So we need to set up the room temperature, which is about the standard laboratory conditions too. Or if you're thinking about tasting the water that is like more like cold water, or even like in hot water, the taste is a little bit different to like in room temperature too. Sometimes the water tastes a little bit sour, so a bit bitter. Okay, it depends on the ions they have, but that also depends on the acidity of the water too. Now, because we are dealing with the K of the water, the equilibrium constant of water, I gotta give you a special the initial for this K. That's known as KW. Okay, now you need to remember this. At 25 degrees Celsius, KW is known as 10 to the power minus 14. Hannah, what does it mean by this value here? How do we interpret the 10 to the power minus 14? It's a very small value. Okay, so what can you tell me about this reaction then? If we have a really small k value, we did that in the beginning of the class today. If we have a really small k value, what does it mean by that? Yeah, tell me. Less product than the reactant. We have not insignificant number of the products formed in that case. This is how you need to interpret related to the module 5 to module 6 again in here. Okay, then if I ask you then, as we have 1 to 1 to 1 to 1 reaction ratio, if 1 mole of the hydronium ion is formed, 1 mole of the hydroxide must be formed too. So can we say the concentration of the hydronium ion at the equilibrium must be same as concentration of the hydroxide ion at the equilibrium too? Everyone agree with that? Because they have the same, if one is formed, as one is formed too. Then, as these two are the same, I'm not going to do the x squared value here. Can we simply say H3O plus at 25 degrees Celsius in the water is 10 to the power minus 7. Okay, same for OH minus will be 10 to the power minus 7 here like this too. At 25, this is for the pure water. I don't have anything else in this case. This is only for the pure water in this case. Does it make sense to all if it's value given? Now, what I don't like to see there is, I don't like to see the 10 to the minus every single time talking about concentration because it's something very difficult to use. Okay, so what we're going to use, we're going to use a symbol of something like P. The P stands for the minus log 10, the logarithms. Okay, the only reason we use a logarithm is we want to get rid of the 10 to the power, so to make it a simple number. So kind of indices, like we want to get to some kind of value indexes. Then what I can do is I can do a P of the H or 3 plus like this. That would be minus log 10 of the 10 to the power minus 7 at the room temperature. Now, as you learn some of the log rules, this is what? 7. As power comes out, cancel out the 10, same base, and cancel out that too. What I don't like to see there is, I don't even want to see that anymore. So what I do, I'm just going to take about this. Oh, hydronium ion is same as the hydrogen ion that formed too. This is called the pH there. This is how we define the pH in chemistry and science. Okay, it simply means that pH is referring to the amount of the concentration of the hydrogen. Oh, not yet. Okay, I give you time to take a photo. I give you more to come. Okay, pH, H stands for the amount of the hydrogen, concentrated hydrogen ion that we have. Okay, remember that I'm talking about at the room temperature, just the pure water. This is why pH water is 7. Does it make sense? Okay, now what about this? We have P of the OH minus then. This would be minus log 10 of the same, 10 to the power minus 7. That would be 7 as well too. As I don't like to see the bracket here, I'm just going to put that into this, POH. We also have something called POH as well too. Now, the final thing is, what I'm going to do is I'm just going to add these two up. Then you get this, pH plus POH where it comes out as 14. This is the rule that you have to remember. So every single time we have a pH and POH added up, it's a sum of the 14. Means that for, let's say we have pH 1, then POH of that solution must be 13, 14 minus 1. If we have pH of the 3, then POH must be 11. Okay, so it won't go over 14 all the times as we're adding up the pH and POH values too. Does it make sense? Okay, this is how you figure out the concentration. Means if you know the pH, guys, this is something that's very important. After that, you can take a photo, Haley. If we know the pH, we are able to know that concentration of the hydronium ion as well too. How do we do that? If the pH, concentration of the hydronium ion, which is same as concentrated hydrogen ion, can be found from, we're going in reverse of the logarithm, that would be 10 to the power minus pH then. Simply means pH 3 has a concentration of the hydrogen ion that 10 to the power minus 3 mole per liter. Does it make sense? Okay. Concentration of the then OH minus hydrogen ion will be 10 to the power minus POH. That would be mole per liter as well too. This might be given on your formula sheet, but I recommend you just memorize it. Just memorize those. It's minus 10 log 10, especially the p value, the minus log 10. Okay, now this is for the pure water at 25 degrees Celsius, which is neutral pH 7, pOH 7. Now, what if we have some different situations? So let's have a look at the page 69, question 1, 2.9a. A, if we use 1 millimole of the sodium hydroxide to 1 liter of the aqueous solution at 25 degrees Celsius, what is the pH of this solution then? Yeah. I'm recording the video. You can screen capture that if you like to, but whatever. Okay, all right. Let's write it down what we have given. We're given that number mole, or just simply find this. Sodium hydroxide concentration can be found by N over V, C equals N over V. Remember that 1 millimole is not moles. Milli means 10 to the power 3 divided by 1 liter gives you 10 to the power minus 3 mole per liter. Okay, what you have to understand is as we have sodium hydroxide aqueous. Do you remember this? Aqueous means it's been hydrated. It's been already separated by the water. So can we say the concentration of this sodium hydroxide is the same as concentration of hydroxide that we have? Does everyone understand why I can write this? I just said sodium hydroxide aqueous means that it's been separated by the sodium water. So it's been like sodiums and hydroxide separated inside. Means if I have a 1 mole of the sodium hydroxide, I must have the same mole of the hydroxide available too. 3 hydroxide available. Does it make sense to all? Okay, this is how we use the solubility to understand the aqueous state again. Then this is given 10 to the power minus 3. We can't find the pH from the OH. So what we have to do, we have to go detour. That we can find the pOH, that is minus log 10 of the OH minus by, which is same as 10 to the power minus 3. That's giving you 3. Detour as in like, as we know the pOH now, as we know the sum of the pOH and pH is 14, pH is simply be 14 minus pOH. That would be 14 minus 3, gives you 11. This is the answer then. So yeah, you can see that it's slightly high, the high pH value of the solution. That's telling you that it's a basic. Okay, or low pH means that it's basic too. Question B. We have 100 mils of the nitric acid solution with the pH of 4. We diluted the solution by adding water to get the total volume of the 1 liter. What is the pH of the diluted solution? So it's been a while you did dilution. Remember that as you, even if you dilute it, you don't really change the number of moles that you have. Does it make sense? Okay, I probably show like some the vitamin C like tablets. I add some more water, get some more diluted, but it doesn't mean like I get the less amount of vitamin C. I still get the same amount. I just need to drink a lot to get the same amount in that case. So 100 mils nitric acid pOH. So let's start from here. The pH is given as 4.0, means that the concentration of the nitric acid, or the hydronium ion can be found by 10 to the power minus 4 mole per liter straight away. Isn't this same as concentration of nitric acid as well too? Yeah, because nitric acid is being separated, so as I said, same acid amount. The only case difference is when we have a diprotic and triprotic. You have to count differently for those number of moles. So showing that HNO3, or you can show like plus H2O, forming that H3O plus NO3 minus, if you like to show that unbalanced chemical equations. Okay, now after you got to this point over here, you get the new you got to find a new concentration, because what you have done, we have done is we mix it up to get the total volume of the 1 liter from 100 mils. So time to bring it out. C1, V1 equals to C2, V2. The new concentration C2 can be found by C1, V1 over V2. Concentration, initial concentration that we had is 10 to the power minus 4. That times that volume of the 100 mils, so 0.1, divided by new volume of the 1 liter, gives you 10 to the power minus 5 mole per liter. That's the new concentration of the nitric acid, which is diluted. Then pH, which is minus log 10 of the given amount. That'll be simply 5. That's it. So what you see there is from pH 4, now it's been increased to pH 5. Oh, sorry, 2 sig 5.0. Oh, I forgot to tell you. For the log value, okay, if we have the pH minus log, say this, okay, this is not a 2 sig fig, it's a 1 sig fig. Please remember that. For the logarithms, okay, we do not count the numbers at the front and before the numbers. There's something that confuses you a lot. 5.10 in logarithm, which is the pH, is 1 sig fig, not 2. This is a rule that you need to remember. There was a case who lost the markers of the wrong sig fig from the pH. The sig fig given was a 2. If there's 2 sig figs given, then you need to write an 5.00 in 2 sig figs like this. That we only count these as a sig fig in their logarithms. Okay? 3 more minutes. Anna, 3 more minutes. Does it make sense? Okay, we'll probably come back to this again later on too about the sig figs and errors. It's better you make the mistake in here I can fix you that sig figs, but please remember that the log, we do not count the number at the front. Okay, all right, let's do one more. Actually, 2. Calculate pH and pOH of a solution in which the concentration of the hydronium ion is 0.14. Give your answer in the 2 decimal places. So what we have is the concentration of the hydronium ion. That's given as 0.14, question C. Okay. That means we are able to find the pH by minus log 10 of the hydronium ion. That's minus log 10 of the 0.14. Use calculator, log 0.14, you get 0.85 in 2 decimal points. As question indicates, 2 decimal points. Okay, then pOH is simply be 14 minus pH, that is 13.15 in 2 decimal points. Okay, D. What is the pH and pOH of the barium hydroxide? Okay, give it a go. Give it 1 minute to try the question D. Make sure you follow the 1 sig fig value, guys. Okay, barium hydroxide is actually divided into the barium 2 plus with the 2 hydroxide ion. Remember this. This is what I mean by if you're given something that have different values of the hydroxide compared to the given value, you got to consider about in the reaction ratio. That this means if the concentration of the barium hydroxide is given as 0.005 mole per liter, then concentration of hydroxide is twice of that. 2 times 0.005, that's 0.010 mole per liter according to the reaction ratio. and the rest is pretty much the same. Then POH, which is same as log 10 of the hydroxide ion concentration is minus log 10 of the 0.01. That is log 0.01, you get 2. Okay, 2.0, 1 sig fig. This is 1 sig fig. Again, we don't count the number at the front and before the dot. When you count the decimals as a sig figs, then therefore pH must be 14 minus 2 gives you 12.0. This is 1 sig fig as well too. Okay, that's how you need to deal with the pH and pH. Just playing around the numbers and to get the concentration, the hydronium ions and some hydroxide ions. Any questions up to here? We are going to finish up to chapter 3 next week. I'm going to practice more some calculation involving like acid and base reactions. I'm going to bring back some K values too. Yes, and ice tables. Yes, we do the ice tables in module 6, so let's get prepared for that. All right, homework next week. The homework is uploaded on your class 365 as well, so you can download that. But for those, come here and give you prints. No. Okay.
That's what my mod.
Okay, that's it.
It's like,